Hello, everyone. Today I'm going to present false discovery rate and exceedance control in high-dimensional linear models. The motivating example is an HIV-DB dataset, which contains drug resistance measurements and the presence of mutations in HIV that might be associated with it. The response is the sample's log-fold increase of lab-tested resistance to a certain drug. And the candidate predictors are binary variables indicating whether or not the sample has some mutations. And the question is to detect relevant mutations that are truly associated with the drug resistance and to ensure that most of the selected mutations are true discoveries. So statistically, we form the problem into a high-dimensional linear model. And to control the number of false discoveries, a popular target is the false discovery rate, FDR, which is the expected false discovery proportion. But in practice, it might be more important to control false discovery exceedance in addition to FDR. The false discovery exceedance says that we control the probability that FDP is smaller than some level alpha with probability at least P0. And since researchers usually have only one dataset based on which variables are selected, they obtain a realized FDP, and therefore it might be more important to control the FDP exceedance rather than FDR. In our method, we simultaneously control FDR and FDP exceedance. We do so by defining the discoveries as those beta i's that are non-zero in the solution vector of a constraint optimization problem. The loss function is a sorted L1 norm, where larger beta i's receive larger penalty lambda I. And the constraint is that the solution vector beta should not be too far away from the posterior mean beta hat. And we assume sparsity, which is the number of non-zero elements in the ground truth, is small relative to the total number of predictors P. It turns out that this two-way quantification of false discovery control yields numerically improved performance in terms of FDP over popular alternatives. In the motivate